All right, question 15. Proof by contradiction. With some of these proofs, it's often worth just taking a look at it and just looking at some examples just to make sure you know what's going on here. So he's talking about square numbers, one less than square numbers, whether they're prime or not. So if we just write down a few square numbers, so we've got 4, 9, 16, 25, 36, and so on. If we subtract 1 from those, the question is saying that the only time you get a prime when you do a square number minus 1 is this example here, when the prime number is 3. So I mean it's looking like this is going to be true, isn't it? But in order to prove this, in order to prove that none of these values are prime, what we have to do is do a proof by contradiction here. All right, so as usual with the proof by contradiction, you assume the opposite. Okay, so we're trying to show that these are always not prime. So let's assume these are prime. So assume that P is a prime number which is less than is one less than a square number. Okay, so therefore P will equal a square number minus 1, where n is a positive integer. And it's got to be greater than 1, because if n was equal to 1, we'd just get 0. So that's obviously couldn't possibly be prime. So n would have to be greater than 1. So if we the key to this question is factorizing this. Now when n equals 2, we get this is 3 times 1, and so we get the prime number 3, which is fine. That's not a contradiction. But when n is greater than when n is greater than 2, this value here, this prime, is going to be an integer times by another integer, and both of those integers are going to be greater than 1. So therefore P can't possibly be a prime number, and that will be a contradiction. So to write this down, when n is greater than 2, P has two factors. P has two factors, which are n plus 1 and n minus 1. And since n is greater than 2, these are both greater than 1. And so P cannot be prime. P is not prime. But that is a contradiction. That's the symbol for a contradiction, because we assumed up here that P was prime, but it turns out that P can't be prime. So that's a contradiction, and therefore the original statement must be true. The original statement is true. So by original statement, I mean this one given in the question. So that's our proof by contradiction finished.